I have two things to talk about today. And these two things are really important. If you can understand the essence of today's lecture, actually you can go to many different control designs in modern control theory. The topic today is about observers and observer state feedback control. We are actually introducing more and more about controls. Observer, the concept is quite relatively intuitive. You guys all know about what it means to try to estimate something. And this observer is just a special estimator of the states. And then observer state feedback control, this is really powerful. If you can understand this, then you can go to the perhaps most popular modern control method implemented, which is linear quadratic Gaussian. Is just a special observer state feedback control. Let's dive into the technical details of these two concepts. There are generally two kinds of observers I want to introduce to you. The motivation is quite simple. Usually, when we are given a system state equation, whether continuous time or discrete time, we only get indirect measurement of the states, y equals to cx. C can be a row vector, in that case. All the state information, state is a vector, is condensed into c times x, a scalar. So full state feedback is usually not available. We can only see some information about the states from the output. But we all know that if we can have access to the full state, really powerful control design can be implemented. We can have state feedback control, which can place the eigenvalues of the closed loop arbitrarily in the complex plane. So how can we do? We can do a state estimation problem to try to estimate the state x based on the limited output y. The deterministic case of state estimation is what we're going to focus on today, is the observer design concept. Deterministic means there are no noises that we directly consider in the system dynamics. And in the stochastic case, where we assume there are sensor noises and the states can have noises too, the input can have different kinds of noises in here. And then, let's say, if we don't have these noise terms, W in the state equation side and N in the measurement equation side, it's a deterministic state estimation problem. And if we consider these, then we will have stochastic state estimation problem. The most frequent option in this category is the Kalman filter, which is a milestone in modern control theory. It is actually, the intuition is quite straightforward if we look at the state equation, either in continuous time, x dot equals ax plus bu, or in the discrete time, xk plus 1 equals axk plus buk. It is seemingly intuitive to design, if we want to estimate x and we know the input u, we can all know these terms. It seems natural to design an estimate of the state. We call it x hat. And in the continuous time case, I am just going to copy down these dynamics in the state equation. I say x hat dot equals ax hat plus but. I drive this estimator with the same amount of input u, and the thing is the same in the discrete time case. I use the same control input to drive the state dynamics. If I know A and B, then it seems intuitive that I can get an estimate x hat from these. We don't know the initial state, x0, so we have to, for this is the dynamic equation, we need to initialize it as well. So we just do the best estimate that we can about the initial state. So we can say x hat 0 is the best estimate that we can have for the initial state. Usually we set it to 0 if we don't have any good idea about where the initial state is. However, there is some problem over here. The problem relates to let's talk about the accuracy of this estimator. Let's talk about how the difference or the error between the true state and the estimated states, let's define it as E, which is x minus x hat. Let us see how this error actually evolves. We know the initial error, right? The initial error is the difference between the true state x0 minus my estimated state x hat 0. And if we do the subtraction between these two, the same amount of input will cancel out. And then if we subtract on the left-hand side, we're going to have the derivative of x minus x hat, which is going to be the derivative of the error, will equal to ax minus ax hat. The BU term gets canceled out. So I'm remaining as ax minus x hat, which is a times e. This is the aerodynamics in the continuous time case. The situation is the same if we consider the discrete time case. The input term cancels out, and then the left-hand side, by subtraction, we get the error at time k plus 1, and the right-hand side, I get a times the difference between x and x hat at time k. So these are the aerodynamics. Some problem immediately appears because the eigenvalues of A in the continuous time case, if the eigenvalues of A have components on the right-hand side, then we are screwed. This arrow will go to infinity in the end. And if the eigenvalue of the A matrix in the discrete time case have magnitude larger than 1, then we are also screwed. So this thing cannot work because the eigenvalues of A is not guaranteed to be stable. In other words, if A is not Hurwitz in the continuous time case or Skur in the discrete time case, then the arrow will diverge. Another thing that is also very important is in here, we talked about in practice, actually nothing is deterministic. There are always some small errors in here. If there are these kind of input disturbances, then there will be some extra term over here and over here. Then the aerodynamics is going to be quite sensitive to these errors. So, in summary, open loop, this is an open loop observer, right? There's no feedback. Open loop observers, they look simple, but they cannot work in practice and can actually be very dangerous to implement in practice. What we do is this concept called closed loop or Luenberger observer. The concept is very simple. Instead of just doing a direct copy of the plant, which is what we did previously, we just add one small thing, and then the entire story will be changed. We add the difference between the actual output y and the output that comes from this copy of the plant. In other words, this is an estimate of the output. If everything goes right, if my state is correctly estimated, then the output will be similar between this line, and the error will be small. But if there are some incorrect initial estimates, then this error will have some non-zero value, and we can use this to improve the state estimation part. And that is a closed loop observer now, because we are effectively using some feedback from the actual system and the estimated output. All right? This is called a Luenberger observer. David Luenberger, full name, is a professor from Stanford. He actually retired not long ago in 2013. He attended Caltech for his bachelor's degree, and he attended his PhD at Stanford. In his PhD thesis, he looked into the observer design, and then he discovered something that's pretty innovative, and the closed-loop observer was named after him. That's the basic concepts, but let us put these concepts into actual practice. Let us see how we can mathematically realize this closed-loop observer concept. We have the same thing. We have a copy of the system dynamics, AX hat plus BU, same thing here. We copy AB dynamics into here. The difference is we now add an arrow term, which is the difference between the actual output Y and the estimated output Y coming out of the observer. If we have the system dynamics Y equals CX, the true output is this, then the estimated output Y hat will be CX hat. We use this arrow term to drive this state estimator. If we put the actual Y hat values into here, then we can have AX hat plus BU plus L times the difference between Y and CX hat. Same thing, we need to initialize this estimator, and usually we just initialize it to be 0. Now, with this one, we can do some analysis. We see that there are two X hat terms. We can combine them, AX hat minus LCX hat. And then there is this BU plus LY term. The two X hats can be combined together, and the new scaling element in front of X hat is going to be A minus LC. Then these are the additional terms going into the observer. We talked about why the open loop observer doesn't work, because we analyzed the error dynamics, right? We thought the error dynamics is not guaranteed to converge to 0. Let's take a look at the new thing now, how the error dynamics for this closed loop observer works. We have the state dynamics, we have the observer dynamics. I'm just copying the same equation down over here. If we define the same thing, X minus X hat to be the error in the state estimation problem, then we can have same thing, subtract this equation with this equation. On the left-hand side, we will have X dot minus X hat dot. And on the right-hand side, we will have A X plus BU minus A minus LC X hat plus LY plus BU. Some terms is going to cancel out, and then some terms can be combined. This BU term cancels out. This is going to be a minus sign over here. So the BU term gets canceled out. And then we have an AX over here. We have an AX hat over here. So we will have A times X minus X hat, which is A times E. And then we will have, so this equals AX minus X hat minus plus LCX hat minus LY. So this is AE. And then the remaining part is actually also very easy to combine. They have the same L term, and Y is C times X over here. So we're going to have minus L. If we substitute Y equals CX over here and then combine these two, we're going to have minus LC arrow. And then these two combined together becomes A minus LC times E. In this case, we can see that we can actually change the aerodynamics, right? Giving an A and giving a C, we can design L to change the closed loop eigenvalues over here. So that's good. We have the control. If all the eigenvalues of this observer closed loop matrix are on the left half plane, then the aerodynamics can be made asymptotically stable. That means regardless of the initial arrow, then eventually we're going to have a correct estimate of the state. That's quite nice. Now there's something more actually about it. If AC is in the observer canonical form, or in general, if AC, as long as they are an observer pair, they construct a full rank n observability matrix, then we can place all the eigenvalues of A minus LC arbitrarily. This arbitrary we need to be a little bit more careful. This arbitrary assignment means if we have complex eigenvalues, then they have to at least come in pairs, right? So it has to be symmetric with respect to the real axis of the complex plane if there are complex eigenvalues. This is a theorem, and it's very easy to see. Let's start with the observable canonical form. Let's say A is in the observable canonical form that look like this. Only the first column has these coefficients A, alpha 0 to alpha n minus 1. And then C is in the observable canonical form. That means C is 1, 0, 0, 0, 0, etc. Let's start with this case, and then we're going to talk about the case when they are not observable canonical forms. Some quick observations. If A is in the observable canonical form, we know that the determinant of Si minus A, which will be dependent on only the first column of the coefficients of A. Actually, it's Sn alpha n minus 1, Sn minus 1, all the way to alpha 1s plus alpha 0. That's a fact. Our goal is to place the eigenvalues of A minus LC in this Luenberger observer at, let's pick some locations. Let's say P1 bar to Pn bar. We want to place the eigenvalues to P1 bar to Pn bar. That simply means this. We want to design determinant of Si minus A minus LC to be the product between S minus all these closed loop eigenvalues. Let's say this product, if you give me P1 bar to Pn bar, then I can compute the coefficients for this polynomial, gamma bar. Right? That's our goal. You give me P1 bar and Pn bar, I'm going to tell you L. Let's say L is a vector. Let's say it's L0, L1, and then all the way to Ln minus 1. It is a column vector. It is a skinny matrix, tall, skinny matrix, because C is a wide matrix. And then for this to work, for this A minus LC, this dimension to work, L must be a tall matrix like this, and then you multiply a wide matrix like this. That's the dimension. Now, we said the matrix A and C, they are in observable canonical form. So if you pay attention to such fact, you can see LC becomes very structured. L is this column vector, C is a row vector. We consider the single output case. Then this product multiplied together, you can see only the first column has values. All the remaining columns will be 0 after this vector product. So that means, remember, A in the observable canonical form, dynamics of A comes from these only the first column of the A matrix. Now, A only has the first column to be relevant. A minus LC, you can see it's going to become also very structured. It's going to be negative alpha n minus 1 minus L0, negative alpha n minus 2 minus L1, all the way down to the bottom, negative alpha 0 minus L n minus 1. This side doesn't change. So that means A and A minus LC have the same structure. And then A, recall, the eigenvalue of A coming out of this characteristic equation has this property, right? The determinant of Si minus A equals determined only from the first column is this form. And we said this is our goal. We want the determinant of Si minus this observer closed loop matrix to be in this form. The coefficients are, the target values are gamma bar n minus 1 and then all the way to gamma bar 0. That's our target. Because this A and A minus LC, they have the same structure, right? We actually don't need to do the matrix algebra. We don't need to do the linear algebra and use the formula to compute the determinant of this. We can actually directly read out, because they have same structures, we can know that this determinant is going to be Sn plus the negative of the 1, 1 entry here, which is alpha n minus 1 plus L0 times Sn minus 1. And then all the way, the last constant term in this determinant computation is going to be the negative of the last element in the first column, which is alpha 0 plus Ln minus 1. We have a target, and we know that the A matrix, the coefficients alpha, we want to determine L. Then the result is actually very simple. L is going to be the difference between the target value and the dynamics of the A matrix, alpha n minus 1. All right? So if the system dynamics is in the observable canonical form, then observer design is extremely easy. There's no complex algebra. It's just a simple subtraction. Now, if the system dynamics is not in observable canonical form, then we can transform it into the observable canonical form, right? So let's call this is the original system dynamic equation. After a similarity transform, x equal to R inverse x OB, observable state, then we have x dot OB equals A sub O x OB plus B sub O U, and then same thing for the output equation y. Then this is in observable canonical form, so we can use the previous formula on this, right? So let's just focus on this new state equation, and then we can use the previous formula to estimate this x sub OB. Let's call it x hat OB. We do the observer design, and we determine this L tilde using the previous subtraction form of the calculation to get XL tilde. Once we get L tilde, we can go back to the original state space and compute the observer gain L for this original state. That is not difficult as well, because once we design L tilde for this state equation after the similarity transform, then this is nothing but we know that x and xob has this relationship, static relationship. So xob hat simply means r times x d dt. So therefore, we can write it simply. The left-hand side is therefore nothing but r times x hat dot. And then the right-hand side, we know AO, right, which is RA, R inverse, And L tilde is what we calculate. And then CO is from the similarity transform as well. It's C times R inverse. And then X hat OB using this similarity transform is nothing but R times X. So R times X hat. So this is R X hat, and then the remaining is the same. BO, substituting BO equals RB. This equation will become this. Okay? This is what we want in the end, X hat, right? So let's remove R matrix from the left-hand side. This is very easy to do. Just multiply R inverse on the left. Then the right-hand side becomes, this is gonna get canceled. And then L tilde in the front is gonna be multiplied with R inverse. And then this R inverse over here is actually going to disappear as well because they multiply with this R over here. So do this very simple matrix multiplication, then we can arrive at this implementable form of the state estimate for X, the original system states, instead of the observable system states after the similarity transform. And the powerful fact, again, is that if the system is in observable canonical form, we know that X tilde can place the eigenvalue of this matrix arbitrarily. Then, because a similarity transform doesn't change the eigenvalues, because R is invertible. So the original state equation, if we design observers in this way, all the observed eigenvalues can be arbitrarily placed. That's a powerful fact. So Luenberger observers very easy to design and implement, and very powerful as well. The implementation in block diagram is as follows. We have, I'm just writing the state equation in a little bit more details. This is the system equation. And then we have a copy of the system equation. And then we use the difference between the actual output Y and the estimated output Y hat from the observer. The difference is going to be driving the state estimate X hat. And then the only thing that we need to compute is this observer gain, L. That is the continuous time Luenberger observer design. When we implement in this way, we have actually the order of this entire system is going to change. The order of this system is, let's say, nth order. Then this observed state is also going to have its dynamics. We have a copy of the system over here. The order of the entire thing is actually 2 times n. Sometimes we say this augmented system, we can write it in a single state equation. Previously, we write the system dynamics separately. We write the observer dynamics separately. We can write them all together in one lumped augmented state equation. That's very easy to do. So the new state vector is going to be X and X hat. And then we just put them together, stack them together, both on the left and on the right. We have X hat, X dot equals A times X, so it's A times X plus 0 times X hat plus B times U. And X hat dot, it equals A minus LC X hat plus LCX over here, then plus BU. That's the augmented system. And we can see the eigenvalues of this augmented system. This matrix is lower triangular. So the eigenvalues come from the eigenvalues of A and the eigenvalues of A minus LC. Okay? We can also write it the slightly in a different way. This time, the eigenvalue will be even more obvious. We can write it in a way to have, is actually after similarity transform. We use X and the arrow, observer arrow, E, as the second set of states over here. If we do that, then the augmented system equation is further simplified. We still have X dot equals AX plus BU, and we previously analyzed that E, the aerodynamics, E dot equals A minus LC times E. That's it. If we look at the augmented system this way, we can see even clearly that the eigenvalues come from just these two. We don't change the state dynamics. The eigenvalues of the original system doesn't change. We can change the observer eigenvalues arbitrarily if it's observable system. All right? And the underlying similarity transform between this form of the augmented system and this form is very easy. We know that arrow equals X minus X hat. So E equals identity matrix times X minus identity matrix times X hat. That is the similarity transform. This is an invertible matrix, so it defines a similarity transform.